Hi, my name is Kevin Starr, and in this session of single loop control methods, we're going to talk about dealing with nonlinearities. Nonlinearities are kind of difficult to deal with, but ignoring them is futile. Everything has some measure of a nonlinearity. What we've talked about up to now is linear. A linear response is if I make a change, I get an output, and I get the same measurement change for an output change every single time. So if I look at it today, tomorrow, or next year, it's always the same. In the real world, that just isn't the case. Now what we've looked at so far is we've got this control loop where we have our controller talking to an I to P converter, which talks to a valve, which changes the process, changes maybe an orifice placed or something like that, a transducer that converts that back into a measurement. So you literally have this system here, this control loop. And this could be a flow, pressure, temperature, level, whatever. You have those attributes, a controller to a pressure converter to a valve positioner. It changes the process changes some transducer. So we have this loop. So my question is where can nonlinear responses or nonlinearities show up in any one of those processes? So what I want to do is just shade in the areas where nonlinearities can occur. So can they control in the controller? Where can they occur? For just a second, boom. Everywhere they can show up. Nonlinearities can show up in the controller, the process, the I to P, the valve, the sense. And so these are those question marks that we talked about. The number of unknowns in your process dynamics is really unlimited. So when we start, we try to minimize the effect of nonlinearities and just look for the big components. But every actuator has a nonlinear action. Every process, they're all over the place. So I'm just going to show you a couple of examples and some of the big ones and how to deal with those. By starting with some of the older controllers have what's called a deadband. It can come in different spots. It can be in the measurement, it can be in the controller, it can be in the signal. There's a dead zone. And basically what happens is the controller doesn't do anything while it thinks it's in the deadband. And what results is a limit cycle. A limit cycle is when you have a nonlinearity that is causing the process to bang back and forth. So it literally hits the top. I've heard it explained like you're driving down the road in a car and you only open your eyes when your right wheels hit the right berm, and then you make an adjustment, and then you open your eyes when your left wheels hit the left berm. So you can kind of imagine you would just, you only open your eyes when you're in trouble. Dead bands and dead zones can cause that. Some of our older controllers had these big, huge dead bands, and sometimes they're appropriate if your minimum output can't move the process small enough. Well, then you can't output smaller than the minimum on time. In those cases, that's about the only time I would recommend a dead band. But most of the time, you want your dead band as small as possible, if not zero. In order to get to this poor guy, he's only allowed to open his eyes when he gets to the peak. This is the idea. He'll be going back and forth. He climbs up the mountain, but when he gets to the peak, he has to close his eyes. That's what a limit cycle is. As you'll see there's a lot of self-imposed limit cycles that can come with dead bands on the error, dead bands on the measurement, dead bands in the signal conditioning, or it can even be the actuator, and I'll show you an example of that. In order to hit the target, we have to remove those constraints. We have to get our eyes focused on the target, and that's not by hiding it with a dead band of any type. Another one, a nonlinearity can come in, is in the process gain. And notice what happens here. Notice each of these steps in the output are the same size. Okay, this is an example. This would be kind of hard to do this on a running process, but notice the process. Over here I made a change and it moved just a little bit. Here I moved more, and then it moved a lot. So this is where we've got a nonlinear process gain. The process literally changes a different amount depending upon the same change in the actuation device. There's several reasons that you can get this. For example, imagine a tank that's laying on its side, a cylinder. Well, once you get around the diameter, your process gain will change a lot depending on where the level's at. That's just a function of the process. I've seen actuators that have ranges. They have what's called an S-curve or a drive. I've heard the rule, 10-90, 30-60 rule. That says your valve needs to operate between 30 and 60%, and you roughly have 10 to 90% of your operating range. So at 30% actuator, you're at 10% of your range. At 60% of your actuator, you're at 90. So I call it the 30-10-60-90 rule. A lot of times when I walk into a facility and I'm getting ready to tune it, I look at the history to see where that actuator's been operating at. If it's operating around 70%, I only have 10% of the range left, which means I'm going to have a rough day. If I've seen that sometimes it operates around 60%, that's right in the middle, it's going to be fairly linear in its operating range. These are the type of things that you need to identify to say, well, maybe it's a nonlinear response, but it's consistent depending on where it's at. When that happens, gain scheduling, adaptive control, those make sense. But don't start there. Look to see if you can come up with a tuning number. Pick the biggest one, and it will be the biggest process gain, and that'll work for all the cases. But don't ignore that this can happen. I've been to a place where on some particular runs, they ran the valve at 70%. Other ones, they ran it at 50%. When I did a bump test in both cases, the gain was 10 times different. So there wasn't a number that would fit the entire operating range of that particular process. So we came up with adaptive control that looked at the valve position. Said, oh, well, if you're up here, use these tuning numbers. If you're down here, use these, and it worked fine. This is one that you'll see in terms of classic symptoms of what we call a bad valve or a sticky valve, where what we have is the set point is not moving, but the measurement, it's up and then it's down, and it's up and then it's down. And traditionally, they'll look like a square wave. And so you can see here, you've got this sort of a square wave pattern in the measurement. And if you look at the output, you have what's called a triangle wave. So if you think about the best way, if you can imagine a single-seated globe valve, it's the top hat has a diaphragm connected to a shaft, and you're filling air in it. So let's say the shaft is rusty. So now you're filling it up, the air you're building pressure, and it's trying to push on that stem, but there's rust in the way. And then all of a sudden, the air pressure builds, and it goes, and it jumps right past the rust, and it says, okay, now I'm there. Well, then what happens is you get this big rush of process because your actuator just moved. Well, now your controller's like, oops, I've got an error, so it starts trying to reduce the air pressure to pull that stem back up, but now it's stuck again. They call that static friction or stiction. So stiction gets stuck, and what happens is you'll get this, it's called a limit cycle again because it's cycling. But the classic symptoms are a square wave in the measurement and a triangle wave in the output. Now, if it happens to be a tank, you'll get a triangle wave in the measurement and a triangle wave in the output. That's what makes it kind of difficult. But if it's self-regulating, you'll get a square wave in the measurement and a triangle wave in the output. If it's an integrating process, you'll get a triangle wave in the measurement and a triangle wave in the output. But it's a limit cycle. Whenever I see these, if I flip control off, it'll stop. If I turn it on, it starts again. I'll go and look at the actuator, and if it has a valve positioner, you'll see it, kind of jump back and forth. A lot of times that's just a sign that the valve positioner is wore out. They usually have a cam on them, and maybe they're stuck. Or maybe it's got fingers or gears that get stuck, and they break. Those are things that need to be fixed mechanically. You can't fix that with process control or by adding a deadband. So in this is just a simple case where we've touched on dead times that may be coming from the control, dead zones, which may be coming from the measurement, valve gains, which may be coming from the process, and stiction or static friction, and overcoming that in your actuation device. In order to tackle these, you actually understanding that not everything works just in a linear fashion. Control theory always works. The application of it may not work if you've ignored one of the nonlinearities that might be present. So just by knowing those few that we talked about, it will help you improve your success rate when you're doing your tuning.